Okay, now I asked, we have this situation, we got charge Q here at the origin. Make things easy, which is in 2 dimensions, we could be in 3. Just add a coordinate, everything is still gonna work out. And we got a point A and a point B, so I want you to tell me everything you can about point A and point B, right? Now, so if you say, okay, distance, well, yeah, easily get the distance, Pythagorean theorem, right? That's good, okay? Um, and, a couple of other things, angles and stuff. Um, so I asked the question, could you get the force? Okay, and I kind of left it at that. Now, to get the force, if they didn't give you charges here, you want to get the force, you better put a charge here at a time. Okay? And since I give you this charge in symbols, this charge QA and this charge QB. So now, QA divided by the square of the distance. Well, 25 and 81 is 96. The units are, okay? Times unit vector in this direction. There's a force. Okay. And what we got? 144, 9, 153. Okay. Now, I haven't said what the units are here, but if you have units, if these are in centimeters or in meters, okay, you have it. In general, if this point is just A1, A2, and this is B1, B2, then you just use the symbols, right? And you could write all this in terms of symbols. If this coordinates are A1, B2, then this would be A1 or A1, A2. And that's what. Yeah, let's call it A1, A2. Then you'd have A1 squared plus A2 squared here, the square root of A1 squared plus the square root of A1 squared plus A2 squared here, and AI plus BJ here, right? That would be a general form for AI plus BJ, A1I plus A2J. Okay. Since I'm using A and B here, I want to use A's for these and B's for these. We could do that in symbols. It would be fine. So I'm just going to write this. Q didn't come out very well. That'd be kind of a general form, and we could just replace the A's with B's. Get this, right? So it's pretty easy. So that's fine. What else can we determine at point A and point B? Have electric field, what are other important quantities that we've dealt with regarding electricity and electrostatic? Okay, ask first, what else can we determine? These points, what other important quantities? I asked, okay, what are the important quantities that we've dealt with in the course so far? Okay, what are the units of some of these quantities? Somebody said joules, okay. And somebody said joules per coulomb. No, that's pretty good. And somebody said volts, yeah, amps, yeah, sort of. Okay. Then I asked, what are these things? What's the name for these things? What is joule a unit of? Okay. Well, work or energy. Okay. What is volt a unit of? There's a name for it. Now, volt is a joule per coulomb. People know that. You know, so like you have been sitting in your thumbs, your brain's been working. Okay. We need to put it together just a little more solidly. And what is the name for what volts measure? And the answer is potential. Now we got the comment, geez, there's potential energy and there's potential. What in the world is the difference? Well, think of the units of a volt. It's a joule per coulomb. The joule is your energy, your coulomb is charge, it's energy per unit of charge or work per unit of charge, right? Potential energy per unit of charge. That's what potential is. Made the analogy with gravitational potential. Okay, we dealt with that. There's a formula for it. It's a very simple formula. All you gotta do is a very, very simple integral. Okay. You just integrate the force from whatever point you're at to infinity, and you get its potential relative to infinity. Okay. Now, whether it's a plus or minus of that, well, I'll let you think that through. But what it comes out to then is in this case, potential energy per unit of charge. Rho for my dummy variable here. So could that be it? You take the integral of the force with respect to rho, okay? And the force would just be the Coulomb force. And I'm sorry, I said we integrate the force, that's the work. I just want to integrate the electric field. Instead of KQ over R squared, I'll use KQ over rho squared because I want R to be my the original position of the particle. We integrate that with respect to rho. Now remember, change of potential energy is the work per unit of charge or per unit of mass if you're in a gravitational field. Okay. So the potential energy is equal and opposite to the work done by the conservative force. Okay. So what's the conservative force? Well, it has magnitude KQ over R squared, which we write as KQ over rho squared because I wanted to use a dummy variable here. Okay. So let's just think about it now. If this is a positive charge, okay, Q here is a positive charge, then your electric field is in the direction toward infinity, isn't it? So that you're doing positive work. And if it's positive work, that means your change of potential energy would be negative of that. It would integrate negative. And that integral is trivial. It's going to be Q over R. You got to get a negative 1 over rho. And you work out the details of the integral. That's just simple. Calculus 2. Integrating 1 over rho squared gives you negative 1 over rho. KQ is just a constant. And then you substitute the lower limit, and actually I kind of think I screwed this up. If we end up with negative KQ over R. Now I'm going to test that, make sure it makes sense, because it's really easy to mess up the negative signs here. This gets a fact that's equal and opposite to the work done. The work done from here to here is going to be positive because the force is pushing that way, assuming Q is a positive charge. Okay. And you're moving that way so that if this is a positive charge, your electric field will be in the direction of your motion. And we get this. If the signs are right. So check out the introductory problem sets, make sure you get the signs right. I'm not gonna say whether that's right or wrong. Okay. And if it's wrong, correct it. Make sure you have it correct. Don't take this as gospel, work it out. Make sure you understand why it's either KQ over R or it's negative KQ. And then make sure it makes sense. Think about this too. You go from closer to further, does your potential energy increase or decrease? Your force is in that direction. Now you're used to gravity. If your force is in this direction and you go this way, potential energy increases, doesn't it? So you want to puzzle that out. If there's an error in the signs here, figure it out. Anyhow, you can find the potential here and here. Okay. You just plug in the R. B. Well, I can use 5 for potential. I'm just going to write KQ over R. Using the numbers here, be KQ over the square root of 96. Potential here would be KQ over the square root of 153. I think it was, right? So what's the potential difference from A to B? If these expressions are correct. Now, this expression doesn't have the negative sign on it, this does. One of them's right, one of them's wrong. Okay? I want you to sort that out. It's always confusing. Okay. Phi A, phi B, potential difference. Well, it will be phi B minus phi A, right? A to B, the change in phi is just to use these numbers. So is that a positive or negative change in potential? Here's your change in potential. Assuming that the negative was wrong here. If the negative is right, it's gonna change its sign. But right now, let's just assume this. Okay, this difference greater than 0 or less than 0. Tell me, greater than or less than? Yeah, it's less than 0 because the square root of 96 is less than the square root of 153. 1 over the smaller number is going to be bigger than 1 over the bigger number, right? Reciprocal of smaller number is bigger. Now, does it make sense? If I move a positive charge from this distance to this distance, does the field do positive or negative work on it? Does negative work because this is further. Okay. Now we could go from here to here on a straight radial line from this distance to this distance. We go straight out to here, then we go along an arc of a circle centered at the origin from here to here, right? Well, your R isn't going to change on that circle. Okay. Also, if you move from here to here along a straight line, well, your motion's in this direction and your field's in this direction. The component of your motion in the straight line is in the same direction as a component of your field, so your field is going to be doing positive work on a positive charge. Okay. You got to think about all those things in order to understand this potential difference. That's potential difference. Okay. So either the negative sign's right here or it's right here. Figure out which, and whichever's wrong, figure out what's wrong with it. Okay. Now, how about the force? Can you write down an expression for the force and just write it down in terms of symbols? A1, A2, V1, V2, 0, 0, Q, QA, QB. You're not calculating anything, are you? Okay. I was worried because these are all symbols. I said you're taking a picture.